Hello everyone and welcome back. We've got another video here for the last section of Chapter 0, what I was calling Section 5 on one-to-one and onto functions. I don't have the book in front of me right now, so I'm pretty sure I'm not skipping a section, although if I am, I'll make a video for that, but I'm basically 100% sure that I haven't done that. In any event, what we've got today is talking about functions or mappings. And these are things that you're used to from as far back as pre-calculus, but how we're dealing with them in this class is a little bit different because a lot of the things that we're used to being able to do, like necessarily in functions in calculus and the like, we can't necessarily do in abstract algebra. At this point, we haven't even gotten everything in algebra set yet, but when we're talking about functions here, we're just talking about functions from one set to another set, so they don't even necessarily have to be functions of numbers or anything like that. So let's actually start off by taking a look at what we mean by a function. This is a definition I'm sure you've seen a lot, and we'll talk about that, and then what we mean about functions being one-to-one and onto. So first up, we've got three definitions here. Our first one is a definition for a function, and we call this a function or a mapping. Mapping is a fairly common word to use in abstract algebra for this concept. So we've got one mapping or a function that goes from one set to another set, and it assigns each element of the first set, which we call, in this case, our domain. Hang on, that's not the right button. Our domain to each one of those an element in our second set, which we call T and is our codomain. Now, here I put or range. Technically, that depends on whether everything in T is an output for something for an input in S. These are fairly common concepts, and I'm sure you've seen them before, even if they haven't been written in general set terms like this. We typically write this, hang on, let me zoom in a little bit, in set terms like that and that. The second one you will no doubt have seen in places like calculus, but the first one is maybe a little bit new. Essentially, we write F colon the first set, which in this case is S, so the domain, and an arrow which outputs into the output set, the codomain or the range. So that's the idea here. That little bit of notation that I just underlined might be the only thing new for you here, but this is what we mean by a function. This video may be short because some of this stuff will be kind of things that you probably are very familiar with. Some of it won't be so much, but that's an example here. Okay. Our next definition is what we mean by a function being one-to-one. Now, this is also something you will have seen in pre-calculus and calculus, where we talk about a function being one-to-one. What that means is there's exactly one input for every output. In other words, if I have an output, only one thing can map to it. I can't have multiple things mapped to the same output. That's what we mean by one-to-one. This second part here that I've written, whenever f of x equals f of y, x equals y, that's how we actually typically wind up proving something is one-to-one. So if we have some function and we know that f of something equals f of something else, we want to be able to show that the things we plugged in originally had to be the same. In other words, so if we start here, we have to be able to get there. And that's usually the way we actually prove function is one-to-one. So we would start with just f of x equals f of y. We don't say what x and y are, and then we go from there to show that x equals y. And maybe we'll do a quick example in the example section below of how we can prove a function is one-to-one. I've got a lot of examples you can see down below. We won't go through full proofs of all of them, but maybe we'll go through one just to see how you prove something's one-to-one and how you prove something's onto. Speaking of which, onto, that means that everything in our codomain here, T, everything in that set is mapped to by some element of the domain. In other words, everything, every possible output, there's an input that goes to it. That's the idea. And here, the way you actually prove it is this statement right here. You'll notice this is a for any statement. So how you go about proving this is you start off by picking an arbitrary T in T. So that's, hang on. That's what you do to start, and then you show, you find, hang on, let me write this. So you find S such that f of s equals t. I want to underline. So you start with some arbitrary t. You can't pick a particular one because it needs to work for every t. And this is the way in general for any proof works. You pick an arbitrary thing of the for any that you're talking about. Here it's an element t in your set, capital T, and then you want to find the next thing that satisfies whatever property is claimed. In this case, it's that you can find an S in S such that S is T. Now you'll notice here this doesn't give you a method of how to actually find S. You have to pick the S that is going to work. Usually what this involves is working backwards. So you'll have your T, you want to work backwards to find out what S had to be to plug in the first place. If you have formulas, that's easy. If something's a little bit more complicated, it's not necessarily so easy, but there are ways. Usually we'll have something sort of like a formula to do this. Okay, and so that's really all there is to our three definitions here. One-to-one and onto are the main things we're going to worry about. Typically, most of the time we're not worried about, like, we're setting things up usually so that the thing is a function already. But what we're going to be looking at here are figuring out whether some function is one-to-one or onto. And you'll notice the next line down, I have a ton of examples. And all of these examples that we've done here, they're not abstract algebra specific. In fact, any of these you could have seen in a pre-calc or a calc class. And here, what I want you to do is figure out whether the functions are one-to-one, onto, both, or neither. You'll notice I have 5. I probably could have come up with a couple more to even make it worse on you and make you cry. But, you know, since you all are home right now and I can't see you cry, I don't get the joy in my heart from that. So, you know, whatever. I'll let you live a happy life for once. All right. So the idea here is we want to figure out, are these one-to-one, onto, both, or neither? Now, you might remember we had at least a couple of things we had a couple of things in calculus for the graphs, how that would work. So for a one-to-one function, you remember, so let me put it over here. So from calc, it's probably actually from pre-calc, but whatever. A function had to pass a certain test. what I'd like is, so it has to pass some kind of test. So go ahead and pause it, see if you can remember. If not, I will answer. So if you're back, it has to pass the vertical line test. What that says is if we have a graph of our function, so these are the calculus versions of this. Don't think that this is necessarily going to apply to any set. But if you have a graph on the xy plane, the function has to pass the vertical line test in order to be a function in the first place. In other words, if you draw a vertical line through the graph, it can only touch the graph at one point. You might remember the other one that's related. The function has to pass another line test. In this one, I'm not going to make you pause because there's only one other thing that we're probably talking about here. The horizontal line test. Horizontal line test to be 1-to-1. And what that means is if you draw a horizontal line through the graph, if it touches the graph in more than one point, the function's not 1-to-1. In fact, there's a similar test for onto. If you draw a horizontal line through your xy plane and there's any place you can draw that line that doesn't touch the graph at all, the function is not onto. In other words, every y value has to be hit. So if you draw a horizontal line at y equals whatever, it has to hit the graph at least one time for it to be onto. And if it hits it more than one time, it's not 1-to-1. So that's the idea here. So you can actually graph these functions that we're talking about over here to see whether these functions are 1-to-1, onto, both, or neither. So let's go ahead and have you pause the video and try and figure out all of these, whether they're 1-to-1, onto, both, or neither. And you can actually draw the graphs if you want. I'll probably maybe sketch them out to the side just to sort of show you what they roughly look like, but most of these you should already know. Okay, so go ahead and do that, and I will be back. And I am back. All right, so let's actually talk about this. The first one, let me put these in red here. Okay, so the first one, f of x equals 2x plus 3. What you should have found for this one is 1-to-1 and onto. So that's our first function. It is both 1-to-1 and onto. It's easy to see why that is. Let's actually take a quick rough sketch of this graph. So f of x equals 2x plus 3. I'm not even going to try to make the slope of this perfect or anything, but it should look something like this. And the thing is, if you actually draw a horizontal line through that graph, it's always going to touch it in exactly one place, right? Let's do one quick example here. Hang on. So I draw that horizontal line. It touches the graph right here. I can move that line up and down. It doesn't change how many times it touches that line. It always touches it exactly once, never more than once, and it never fails to touch it at all. So this one is both 1-to-1 and onto. Okay. The next one, f of x equals x squared plus 1. Let me actually try and draw little arrows to which graph I want, because they won't fit the way I might like them to. The next one, f of x equals x squared minus 1. You can think about this in the line test as well. Here we get a function that is neither one-to-one nor onto. Okay, so that is what x squared minus 1 is like. And let's actually sketch this one out. Oops, let's move over. This one, you could probably already figure what it looks like. X squared minus 1, this is going to be a parabola. It doesn't hit at the origin, but it hits just below the origin. You get something that looks like this. And if you start with horizontal lines here, you'll notice, depending on where you make the horizontal line, it will either hit 2 times, hang on, those look stupid, zero times, or in one particular instance, exactly 1 time. So the idea here is the horizontal line test doesn't do what we would hope it to do. It shows that this function up here fails to be one-to-one, down here fails to be onto. So as long as you have one of those lines doing that, oh man, I messed that up. Well, whatever. I'll fix it. Right? Blue. And we had points there and there. And I need that line there. And now let's... That was the whole point of doing that. All right, so depending on where you are on the graph, it either fails to be actually, let me do it this way. No, that won't work. It either fails to be one-to-one here or onto there. Okay, so that's what you find there in that one. Okay. So this one is neither, is what we find. Okay. The next one, x cubed minus x, this is maybe the only graph I'm not expecting you to know exactly what it looks like right off. You probably had to plug in some values to get this one. And so before we do this, note that this is a cubic. A cubic graph can do a couple of things. If we have y equals x cubed, it goes through the origin. Before that, it sort of slopes. It sort of curves downward like downward opening parabola. It's not a parabola because it's a cubic, but it's sort of that general shape. And on the right, it curves upward like an opening upward parabola. So that's what that y equals x cubed looks like. But x cubed minus x is a little bit different. And let me actually sketch it out here. If you actually want to know exactly what these points are, you'll have to plot them yourself. But I can at least show you part of it here. So the point about this is we have 3 places this function goes through the x-axis. It goes through at -1, at 0, and at 1. And it curves like this in between, and then beyond, hang on, yeah, there we go. It goes up like this, and beyond to the left, it goes down like this. So once we see that, that's our graph here for this one. This one, the graph looks like that. Once you notice that, think about horizontal lines. Do they show us that this is either not one-to-one or not onto or not both? Well, what we see here, onto, it's easy to see that if we draw a horizontal line through the graph anywhere, it's going to hit at least once. But if we draw it at a specific height here, we can see there are places where this will hit the graph more than once. In fact, it's possible to hit it 3 times like we do right here. It's possible to hit it once, twice, or 3 times, either. Any of those. So what we see here then is because of this little section right here, the function is not one-to-one, and so, but we can still draw a horizontal line no matter where the horizontal line is. It touches the graph at least once. So this one is just onto. Onto and onto only. Okay. So we get that. The next one, f of x equals e to the x. I think I've got room over here. If you don't remember exactly how this graph looks, it looks like this. But, you know, if you don't remember how it looks, hopefully you will after this. It is an important graph after all. The graph looks like this, and we will notice that if we try and draw horizontal lines through this, it never hits more than once. So the function is still one-to-one, but there are places that this graph doesn't touch on the y-axis, anything 0 or below. So what that tells us is this one is just one-to-one. So one-to-one only here. Okay. Oh, I drew that in blue. Whatever, it doesn't matter. I wonder if you can change the color. Yes, you can. There we go. All right, learn something new every day. All right, the next thing is the last one, and I'm going to draw, actually I should draw an arrow here. And I'll draw an arrow down here for the sign. And this one is also one that you should know how it looks. And what we get here, let me sketch this out. I don't have to draw too big of a graph here because you all know what sine does. It goes up and down, and up and down. Oops, and oops, that is not right. And over here, goes back up again. And essentially, these places that it curves back are at -1 and 1. And because of what we see here, we see that there are places above and below 1 and -1. Hang on. That never touch the graph at all. And there are places in between that touch it an infinite number of times. There. So we see that this one also, like the x squared one, fails to be either one-to-one or onto. And I don't have room, so let me just write neither there. Okay. All right. So that is what we mean by these functions being one-to-one, onto, or neither, or both. So what I would like us to do here real quick is to prove that that first graph, and this should be relatively easy, prove that that first function, f of x equals 2x plus 3, from the real numbers to the real numbers, is both one-to-one and onto. I'm going to, in fact, write it out here. F of x equals 2x plus 3 is both oops, that always happens. 1-to-1. That was my motorcycle. I like revving it up inside every once in a while. And on 2. If you couldn't hear that, then that joke was kind of stupid, but whatever. I never claimed to be smart. Alright, so here we go. Let's set this up for a proof. And before I make you pause the video, let's go up and remind ourselves how we prove these things. You'll notice for 1-to-1, we want to show what we've got here. Whenever f of x equals f of y, so that's where we're starting. This is essentially an if-then statement. So you say, let x and y be such that f of x equals f of y, and then show somehow that x equals y. Here you can use x1 and x2 if you want, or whatever, it doesn't matter. The next thing we would prove is the onto one, and here remember this is a for any proof, so you start with picking an arbitrary output, so you pick an arbitrary y value in this case, and you find the x that maps to that. This one's a little bit tougher, but it's still not impossible. You can do some side work to figure out exactly what that x value needs to be. Okay, so let's go ahead and have you all work on that. Go ahead and pause the video, and I will sit here and wait silently while you work on it. I'm not doing anything, I'm just waiting. All right, that was a long time, but we are back. So let's go ahead and do this proof. So we have two parts here. One is 1-to-1. That's our first part of this proof. We want to prove that the function is 1-to-1. So essentially here what we want to do is we want to say, suppose f of x equals f of y, or I'll use x1 and x2 because we actually do have a reason to use y separately from x here. Then, just based on our I don't want to cut the colon there. Just based on what our function is, we can plug those in. So we get 2x1 plus 3 equals 2x2 plus 3. And at this point, what is this kind of problem? This is just a middle school algebra problem. So we get 2x1 equals 2x2. If we subtract 3 from both sides, and therefore dividing both sides by 2, we get x1 equals x2, and that is all we needed to do. That is good enough. Oops. We can check that one off. So, 1-to-1, proven. On to, we need a little bit more room, but I think I've got it because I don't have to skip down a line here. I can write out all the way to the side. So here we're going to start with, remember this is a for any proof, so we start with, let y be an element of y be in the reals. So here we're not saying anything about y, just that it's a real number. And then we want to find x such, so let me write this out. We want to find x such that f of x equals y. Now, of course, this can be a little bit tough to do, but let's do a little side work over to the side. Let me put it in blue. Oops. side work. You do these kind of things a lot in these like proofs like this, where we have a for any, like we do right here. So for any, and then there exists after it, because you have to find the thing that you're claiming exists. So you have to do some work to figure out exactly what it is. So here, remember, we want f of x to equal y. So f of x equals y. From there, all we need to know is that f of x is 2x plus 3. That equals y. Subtract 3, divide by 2, we get x equals y minus 3 over 2. This is all we needed here. Now you'll wonder, why can't we do this for any function then? Right? Why aren't all functions onto if we just solve? Well, remember, here we solved because we're allowed to do all those things. There might be times when you would be getting some result that doesn't always work. Here, if y is a real number, subtracting 3, still a real number. Dividing by 2, still a real number. But if you start doing things like you have x squared equals something, and y might be negative, that would be a situation where you don't have everything that you need. Let me make this a little bit bigger because I do have room for it there. Okay, such that, hang on, f of x equals y. If x equals, what did I say, y minus 3 over 2, then f of x equals 2 times y minus 3 over 2 plus 3 equals y, and then we can make, then we can make our check mark again for that one. All right, and so that is all it takes to prove a function is one-to-one and onto. You know, these can be harder depending on what the function is, but that's just a general guideline of what's going on there. How about I do this a little bit different? Let's actually type that out. There we go. There we go. Okay, so that is our proof of those two things. One other thing I want to mention here that the book doesn't mention, but I think is worth noting. Oh, actually, a couple things. First of all, one-to-one. Functions that are one-to-one, I'm not going to use this term very often, but there is another math term for this, and it is called an injection. I only mention this because it might happen if you go to grad school or something that you might hear this term, or the other one for onto, which we say is a surjection. And these are one-to-one and onto are the more commonly used terms, but some professors will use those. Also, if we have something that's both one-to-one and onto, we call that a bijection. So that one is both one-to-one and onto. Okay. I'm not, like I said, I'm not going to typically use those terms. If I happen to, that's what they mean. I'm sure if I actually do use those terms, I would immediately tell you what they meant as well. But that's just for your own purposes or whatever. The last thing I want to mention here is what we call the pigeonhole principle. And there are different versions of this. We're not actually going to prove this or anything. There are different versions, different statements of the pigeonhole principle, but the one that I've usually seen and probably is the most useful for you all is if we have two sets, set S and a set T, and they both have the same number of elements, and it's finite. So this doesn't work if you have an infinite number of elements. Then a function from S to T is one-to-one if and only if it's onto. So in other words, if you have the same number of elements, like if you have over here in your set S, and you have over here in your set T, and in both of these you have the same number of elements, and let's make it, what, 6, and we've got 6 over here as well. So we have 6 elements in each set. What that tells us here is if we try to map these elements in S to the elements in T, if we want to make sure every time we actually hit an element in T, when we're done, like if we make this one go to this one, and this one go to this one, and if we want to hit every single element, we have to use every single element in the starting set. We have to make every single element in the starting set go to exactly one element in the output set, right? So you can't, hang on, this is awkward. There we go, and this one right here. So if you want to hit every element in T, you can't have something in S hit the same element twice, or you'll lose it. You won't hit every element. Likewise, if you want to make every element in S hit, if you want to make every element in T be hit only once by elements in S, then you wind up using every element in T. So that's the idea of the pigeonhole principle. There are related ideas if your set S is bigger than your set T, you can't have a one-to-one function at that point. And if your set T is bigger than your set S, you can't have an onto function. So let me write those out. These are variations on the pigeonhole principle. If this absolute value symbol here, I'm using that to denote the size of the set. You'll hear this as talked about as cardinality or different things. So if the size of S is n, the size of T is m. If n is greater than m, well, here that means we have to use at least one element more than once. So that means f from S to T can't be one-to-one, sorry. Because if you try and make it one-to-one, you're going to have elements left over in S, and you have to assign every element in S to make a function in the first place. And likewise, if m is greater than n, wait, let me see, am I doing this right? Which one did I make? Yeah. If m is greater than n, we don't have enough elements to map in the first place, so this function can't be onto. These are both equivalent to the original pigeonhole principle. In other words, you could use the pigeonhole principle to prove either one of these, and you can use either one of these to prove the pigeonhole principle. But this is, again, something that the book doesn't mention, but it is a thing that is fairly commonly used in math. And let's see here. Hang on. And let's try, and hopefully I left enough room for him. There, that eyebrow there makes him look worried. And he's a pigeon, so he's fat, because that's what pigeons are. Alright, there we go. Fat pigeon. And I don't know, it's not the best in the world. Hang on, let me try and fix his beak a little bit here. The line is actually kind of long, or kind of thick, because I didn't leave myself too much room to draw. But anyway, that's roughly a pigeon. Or, I don't know, something else. I'll do some fancy stuff here to try and make up for the bad pigeon. Wooden slats or whatever. This is like all those movies and TV shows about New York City where the old guys keep pigeons on the roof. There we go. And I mean, you can't even really see the pigeonhole, but you get the idea. There's the pigeon, there's the pigeonhole. So I guess that's it for the video today. If you have any questions, again, as always, you can contact me on Google Hangouts. You can send me an email to ask a question. You can send me an email to request that we meet on for video chat. And if we do that, it'll probably be through Google Meet. And because Zoom messed up for me, like, I don't remember exactly why, but it quit working, so there's that. Anyway, this is it for the video today. I'll be uploading this later, and let me know if you need anything. I'm happy to help. Bye.